Okay, yeah, welcome back to this afternoon session. I just arrived and I'm happy to see so many faces I know. And I'm even more happy that now we have a talk by Raf Cluckers with the title Finiteness and Diophantine Results in Hensel Minimal Structures. Please.
Thank you. Thanks to the organizers for inviting me. Apologies that it's not about decidability where we usually try to define Z or the ring of integers in the structures, but it's rather about counting Z rational points on certain geometric objects and saying that there are not too many, that there are only a few of them. That can be done in several contexts. One of these contexts goes back to a result by Pila-Wilkie that I will present some analogues of later on. And that's in a minimal result of this flavor, that there are not many integral points on certain geometric objects. And to recall it, let me do it as follows. Let X, a subset of R to the n, be definable in an O-minimal structure, and I will recall some of these definitions later. For example, I will briefly recall what I mean by definable and also by O-minimal, but then the result can be stated as an inequality. So if you have a positive epsilon, and then any h is 1, say, you can look at the transcendental part of this definable set, which I will also recall in a minute. You can look at points with rational coordinates lying on that transcendental part, and which can be written as a quotient of two integers, each of which is an absolute value at most h. I will recall it in a minute, but the upper bound is that there is a constant only depending on epsilon times h to this very small power epsilon. So that's a sub-polynomial growth of the number of Q rational points. So let me recall first some of the basic ingredients that go in. So what is the transcendental part of a definable set? That's, by definition, the complement of the algebraic part inside your definable set. For example, if it's the graph of the exponential, there is no algebraic part inside the graph of the exponential, so you would lose nothing. But the algebraic part is defined as a subset of x, consisting, a point of x lies in the algebraic part if and only if you can find a semi-algebraic curve, or if you prefer an algebraic curve that goes through that point that you're looking at, that has locally around that point you look at the real points on that curve, and it has locally, topologically dimension 1, so it's not an isolated point of that curve. And locally also it lies inside your set X. In that case, if you can find a small piece of a real curve that lies completely in X and goes through your point, you say that point belongs to the algebraic part of my set X. Because on algebraic curves there can lie much more than this many rational points, so you have to throw them away. That's the algebraic part, that's the transcendental part, and then as I said in words already, by this I mean points with Q coordinates lying on that set. And here by adding an extra h, I mean the Q points, each of the coordinates can be written as a quotient of integers, and the integers lie between -h and h in the rational number written as a quotient of integers. So before going into recalling O-minimality, let me state a result which is still work in progress in its full generality, but I will list some known and already documented cases just after it. It's work with Halupczok and Vermeulen, and it's actually mimicking this result, but in a non-Archimedean setup, and I will give some concrete examples of that setup after stating the theorem. So this is theorem B, if this was theorem A. And now, for simplicity, I fix the p-adic numbers as a non-Archimedean model or an Archimedean analog structure to the real. to the reals. So let x in qp to the n be definable in a, the general word is Hensel minimal structure, where the O here comes from the order. It's minimal with respect to some ordered viewpoint on the reals. Here it's with some Henselian structure, but the technical word is 1H minimal. So that's the technical variant of that condition. And then exactly you have the same as here. You can mimic the definition of the transcendental part by what I just said, working with the local condition around the point. You can look at Q rational coordinates of height equals h, and again, it's sub-polynomial growth. So I will define Hensel minimality also a bit later. Let me first sketch you what else can be thought of as non-Archimedean analogues of a real setting. You could also think about uniformity in the prime P here, and that leads to also analog situations where you work inside FP, brackets T, for large P.
About the definition of the algebraic part. You maybe it doesn't matter, but do you require the curves to be definable over Q, or can they be definable over
R or over QP? So they really
so
the curves.
Okay, so you include those. Okay.
Yeah. In FPT for large P, you find analogous result just by a uniform version for QP. But what do you count? Because you don't have Q rational points inside this field. But inside this field, the analog of integers are the polynomials over the finite field, and you take the degree with respect to the variable t in each of the coordinates, and you bound it by a number b. So in some sense, you count in a logarithmic way, because if you fix the degree of that polynomial, you have p to the b possible elements lying on your object. So that's a thing. You can also work inside the Laurent series fields over a field of characteristic 0, like the complex numbers.
So I would have thought that the analog of Q would be the rational function.
Yeah, that's why I said this is the analog of the integers, and then you can also look at FPT points inside on your definable set, for example, and then you bound the t degree of both numerator and denominator by the same b, and then yeah. So for x in here, I will also say the t degree of x is less than b, and I mean both the numerator and the denominator can be taken such that you have a small t degree. And you can do the same thing in CT, where you again look at polynomials or rational functions over C, and you bound the degree with respect to C. Of course, here you have maybe an infinite set of polynomials lying on certain geometric objects, while here, if you bound the t degree, your candidate set is always finite, so you have always finiteness of what you want to count. And okay, this is some possible things you can think of as a non-Archimedean geometric situation comparable to the minimal case. Still, before I want to define O minimality and 1H minimality, I want to document the cases that are already fully present in the literature. And that's a list of results. And the first case was when x in qp to the n is what is called subanalytic. And that's the analog in the reals. That structure is typically called Rn. In the p-adics, that structure can be denoted by qpn. That's where you have the field language, and you add predicates or function symbols for restricted analytic functions. That means conversion power series on Zp to the n. And this was in 2015 with Comte and Loeser. So we overcame some of the challenges to make this non-Archimedean. And one of the challenges was that it's completely disconnected, of course. But I will come back to that challenge later. And then it was made uniform in P, recovering also the FPT case for large P, with Forey and Loeser, also in the subanalytic setting. And very interestingly, so that included a large P positive characteristic, but by Bignamini and Kato, they can also do FPT case for small p, for any p, as soon as you only look at the zero locus of analytic functions. For example, the graph of a converging power series on FP on the valuation ring to the n, they can have a similar sub-polynomial bound. And they use different methods here. But it's not for a definable set, so let me cross that. It's for a locus of analytic function. For a locus of analytic functions. There is another situation where theorem B is fully known. That is when the dimension of x is 1. So when it's a curve. Then this is documented already in the initial papers on Hensel minimality, where we introduced that. And in all the settings, in QP, in FPT for large P, and also some analog formulation of bounds regarding CT points. And let me also mention a very interesting variant by Vermeulen from 2025 on arXiv. And that is, instead of taking x inside QP to the n, he can take x inside CP to the n. And he is still working with a curve. Dimension x is 1, so that we are generalizing this case. More generally, you can take x inside any field of mixed, any Henselian valued field of mixed characteristic, and he counts the Q rational points on it. So here you, an Hensel minimum structure on such a field can be much more wild, can be much more rich than on QP itself. And he has the same subpolynomial bounds. This is, you don't have a strategy yet in higher dimensions for that aspect. For the others, it's work in progress also in higher dimensions. Then this dimension x equal 1 case includes, as I said, QP, FPT, and also CT variant by Cantorel, Farfan, and Stout, and Nguyen and Vermeulen. They did variant for CT for the curve case. But how do you proceed? What do you do on CT? Well, on CT, you look at if X is a definable subset of the Laurent series field over C. You don't count, but you take a certain form of dimension of the transcendental part, and you look at polynomial, say, over C of degree at most P, and you look at this dimension in a certain topological way, where maybe not as a risky dimension, but a slightly different dimension, and you bound it. Remember, B is like a logarithm of before. Log h could be compared to log h, and you would bound it by a multiple of B plus D. So the dimension becomes epsilon times B, sorry. Epsilon plus C epsilon. So it's subpolynomial growth in this, for this dimension. That's in a 1H minimal setting, but the last piece of situation that I want to document is when X is still in CT, but I assume again that it's subanalytic. So it comes from an expansion of the ring language together with converging power series on the valuation ring. In that case, we can take the dimension of X to be general. And this is joint work with Benjamin Novikov himself. And we showed that the transcendental part, and then polynomials of bounded degree on that, is actually finite. It's a finite set, so there is no need to take a topological dimension of it, because that would be zero-dimensional. This number is finite. And then we also observed it can grow arbitrarily fast with B. So you need extra conditions if you want to bound it in terms of B. And these extra conditions we could form some Pfaffian relations. So if the power series that are involved satisfy some extra partial differential equations called Pfaffian system of differential equations. So then we obtain an analog of Wilkie's conjecture, namely the counting, not the dimension, but the actual count is a polynomial in B. It can be bounded by polynomial in B, and here it's 2.
So does this find this result? I forgot. Are the hypotheses different from here, or is it?
Yes.
Here
is this 1H minimal hypothesis.
Oh, okay.
So and then it's really necessary. It can really grow.
Okay.
But if it's subanalytic, it's still close to being polynomial because it's coming from a converging power series. So if you cut it off, it becomes closer to being polynomial. It's not really modulo T that you work here. It's exact solutions, but still it becomes polynomial. So it goes into the algebraic part. So you throw away a lot in the subanalytic case. And then this is related to Wilkie's conjecture, where if you have a restricted Pfaffian subset X of R to the n, and Wilkie conjectured that the number of transcendental points QH is actually logarithmic in H to some power. And this is now a theorem by Benjamin Novikov and Zak. They showed this as a special case of a more general conjecture by Wilkie, and they also showed the more general conjecture of Wilkie's.
Who's the third person?
Zak, that's a student, PhD student of Carl Benjamin at the moment. So this is the cases that are fully documented. I want to define now, recall O minimality, and then by some analogy I will define Hensel minimality, and then I want to tell you about the challenges and ingredients that go into proving this result and adapting it, and the new challenges that come up.
Can you lift the back?
Yeah, good idea. So for O minimal structures, I have a question. Should I explain what a structure is on R? Maybe not. For most of you, it's not necessary. But I will define what an O minimal structure is on the real field R, because I'm going to formulate it a little bit differently than what is usually done as definition, and that's to find it more easy to define mass and minimality later on. So this is a definition. A structure on R, on the field R, is called O minimal. If for any definable set X inside a real line, and now comes the different condition, there is a finite set C, also a subset of R. So this finiteness is giving the control on O minimality and on the set X and so on. A finite set X such that belonging for any X in R belonging to X depends only on a finite tuple, namely the tuple of signs of X minus little c, where little c runs in this finite set, capital C. So of course, it's usually one says it's a finite union of points and open intervals. So for this finite set, you can take these points and the endpoints of these intervals, and the sign can be 0, negative, or positive, and that determines whether the little x lies inside big X or not. And now there is an easy definition, which is a first attempt to explain Hensel minimality. You can call it almost H minimality. So if K is a Henselian dilute field with some extra structure, with a structure, such K is called almost H minimal. If for any unary definable set X inside K, any definable unary set X in K, and now we do the same as there. There is a finite set capital C. Now this time a subset of K. And this finite set again will control good properties of the structure, but also it will prepare the set X in a certain way, because we ask the same thing, but we replace the sign map by another map. So you ask the same thing with sign replaced by a map sometimes denoted by RV. It goes from K to K modulo 1 plus the maximal ideal of the valuation ring, and that's a quotient of multiplicative semigroups. It's nothing else than the union of the zero element with the actual quotient of multiplicative groups, 1 plus the maximal ideal. This replacement of the sign map has infinite image. That seems worrying, but in fact the finiteness is still built in because the set that controls the description of the set capital X is still assumed to be finite. So I can spell it out if you want. So belonging for little x to belong to capital X only depends on this finite tuple with the sign map replaced by the RV map. The RV map.
What is this RV map doing?
Yeah, it sees a little bit. In QP, for example, it sees the leading digit, the leading p-adic digit. So it sees the order of that p-adic digit and the coefficient, so to say. And that's because there is a short exact sequence from the residue field to RV and to gamma. So the it combines information from the residue field and the value group. That's why it's called RV also.
So when you say replacing sign with that, that means we're taking the residue of x minus c for each c, or are we just taking the residue, or the RV of each x, or are we taking the RV of x minus c for each c?
You look at this tuple, RV of x minus c, and then c in c. That's a finite tuple.
Okay.
Yeah. And this determines whether little x belongs to capital X or not. Here, on the minimal side, there are a few things that come for free that will not come for free on the Henselian valued field, so we will need some extra technical treatment of this definition in order to make it workable. For example, what comes here for free, that's two aspects. If X is defined using some parameters from R, the set C can be definable using the same parameters as X. It can be defined with a new formula in that structure, but with the same parameters. That's not something that comes automatically here. There is something else that comes automatically here, which is related to that. That is that it also holds automatically in elementary extensions. That's related to having parameter control also. But here we will have to do some technical aspects that I will just summarize as being extra technical aspects to be taken care of to get the real definition of 1H minimality. And then the most important one is the parameter dependence needs to be built in the definition. So if X is definable using some parameters, C should also be definable with some very precise control of the parameters. And these parameters, they come from several kinds. They could be K parameters, helping to define set X, but they could also be a parameter from RV, so a sign condition. Here, this quotient, you could call it RV, capital RV, residue field and value group information combined. And then what do I mean by taking a parameter from RV? I mean actually you fix an element of RV of K, and then you add a predicate to your language that says that the RV map lands precisely there. So that's not really a parameter, that's more like a predicate that you add for that ball. An element of RV gives a ball in K, its inverse image is a ball, and for that ball you give a name as a predicate. And this also needs to be controlled. And then here, this aspect where you allow extra RV parameters to control the dependence, you need to even look a bit deeper. For example, in mixed characteristic, you need to look at 1 plus, for example, p times the maximal ideal, or more generally an integer times the maximal ideal, which is already a bit deeper than just RV, because this is a smaller ideal. It's a smaller subgroup. But actually you need to work with one parameter which can be with arbitrary depth, or lambda times the maximal ideal for some lambda. So there is a little bit of delicate parameter control going on in finding C. And then you get to the definition of 1H. Except that also you need, for the moment we also need to require that in elementary equivalent structures you also can do this. This also does not come for free. Okay, but this gives the flavor. And for the record, this analogy, we found this explanation after that we developed Hensel minimality. It was not like that we looked at this and we said, what can we do to replace the sign map? That was not the initial inspiration. And Hensel minimality was introduced like 3 years ago in work with Vermeulen, Kikuchi, and Halupczok, and myself also. And we believe it's a good framework to do non-Archimedean geometry in characteristic 0, Henselian valued fields. In positive characteristic Henselian valued fields, we have no idea yet what a nice model theoretic approach to geometry could be, to geometry of definable sets. So it's a framework for doing non-Archimedean geometry, and also arithmetic geometry in the sense that you can look at rational points or integer points and try to say that there are not many, as in theorem, as I wanted to do in theorem. What works well in Hensel minimal structures? That's, for example, dimension theory works very well, but also functions are piecewise. CK for any k, you have stratifications, and you can do a bit more than just having CK functions, as I will explain now. Key tool to approach these bounds on rational points is a variant of resolution of singularities, more adapted to this situation, or it's a variant of smoothening of definable sets, and it's more a way of reparametrizing your definable sets instead of doing a real actual resolution of singularities, and I will state it. And the upshot of this reparametrization is that it works much better actually than resolution of singularities in families. It works much better in definable families. Resolution of singularities a la Hironaka works well in some algebraic families, but then it works generically in the family parameter. But in a QP topology, for example, a generic point does not match well in the Zariski sense and in the p-adic topology sense. So for some of the techniques that you really needed here, you need extra flexibility in definable families, and that works good with these parametrizations. And that goes back to Yonding parametrizations, in a variant also given Gromov parametrizations, but then it goes back to that. You can call it CR parametrizations, and it was done in all minimal context by Pila-Wilkie. And let me state it in the Pila-Wilkie context. If X lies in the unit box, the real unit box, it's definable in R to the n. And the dimension, in the minimal sense, of X is m. To make it interesting, you should think of the dimension as interesting being less than n. For such a definable set, and it also works in definable families, but I will just state the absolute statement. There are finitely many CR maps from the open unit box of the corresponding dimension to X. They are finitely many, let's say, and they are CR maps. Such that together they cover the whole set that you want to cover, maybe X. So in a way they smoothen X out, but piecewise, in pieces. And moreover, the CR norm of these maps, which I will write with an index CR, or CR norm, is bounded by a constant, or for convenience just 1 for your favorite normalization of CR norm. So any given R, this exists. Given R, say, you can find finitely many maps, where the number of maps you need depends on R, of course. And this is handy because if you have bounded CR norm and you have a convex domain, the unit box is convex, then you can do Taylor approximation to compare the distance between 2 points. You can do Taylor approximation of degree R because you know the size of the derivatives, it's convex. But in a non-Archimedean setting, Taylor approximation does not come for free, convexity is not there, so you need to have a different formulation, which is work in progress also in the Hensel minimal setting, and in the documented cases it has been implemented. So let's also here take it in a compact unit box. X definable in Zp to the n. Definable in a 1-inch minimal structure or subanalytic if you want it fully documented. And the dimension again equal to n. Then there are again finitely many maps Pi, and now I take a subset Pi, a subset of Zp to the right dimension, Zp to the n, which is a definable subset, but it's not necessarily convexity doesn't help anyway, so it does not need to be equal. Because we cannot rectilinearize it like in the reals, it's easy and visualizable to rectilinearize, here not, but it goes to X. It's a CR map. The CR norm is again 1, but we ask a bit more. There are finitely many of them. Together they cover the whole set X. Their images cover the whole set X. But also we ask that they are TR, not just CR, but TR, by which we mean that they have good Taylor approximation globally. So Phi of X minus the Taylor polynomial of degree cutoff at order R of that same map Phi at any point, any other point Y, evaluated at X. This difference in the Bjerregaard norm should be at most, because the CR norm is taken to be 1 at most, so it's xy times, usually there is an alpha derivative here, which is bounded by 1 to the power r. So that's a global kind of Taylor approximation for any tuples inside Pi in the domain. Here, this is an adaptation P-adic, you could also do it over CT. Here were a few challenges involved. For example, in this totally disconnects non-convex setting, you can still imagine that you have very locally some Taylor approximation, piecewise locally. So you have to find a way to go from local to piecewise in this non-Archimedean setting. That's one challenge. Another challenge that I will write over there is related to the non-analyticity. In the subanalytic case, you have piecewise analyticity of definable functions. But in a Hensel minimal case, you have an axiomatic framework. So you cannot use and you don't have local analyticity at all. You have to work axiomatically. And if you have some local analyticity, that gives you for free some control locally for Taylor approximation, but also on the size of the derivatives. And I can give a very simple example of that. If you have the valuation ring of CP, you can also do it for other algebraically closed Henselian value fields, to O of CP, and if it's given by a single converging power series, then by comparing the Gauss norm with the sup norm, you already know that the CR norm is at most 1 for free. So just looking at the size of the domain and the size of the image, you get bounds on the CR norm, and you get also Taylor approximation for free. So locally, analyticity gives you these two more or less for free if you can reduce to a situation of converging power series. It also works in higher dimension. So these two become two challenges, together with going from local piecewise, the third challenge in this axiomatic framework. I will erase.
Sorry, what's the Taylor
Yes?
expression on y, of this phi?
Yes. Can you ask it again?
So in this,
Yes.
when you say you can, for any x and y, so
Yes.
what's the Taylor T or, yeah.
So you have your function at x,
Yes.
and you take the polynomial, the Taylor polynomial at some point y. So you compute the Taylor polynomial at y. So that's f of y, the function of y, plus the derivative of the function at y times x minus y, and so on. And that polynomial, that Taylor polynomial cut off at degree r, you evaluate at the tuple x. So it becomes a polynomial in x, but the derivatives of at y come up.
Okay.
So we don't expect much rational points in a transcendental setting. Let me give a few extra remarks. One can, by the same methods, one typically bounds algebraic points instead of Q points. If you bound the height and at the same time you bound the degree of the coordinates over Q. If you bound the degree and the height at the same time, then you can still find c to the epsilon, h to the epsilon bounds, where you have fixed the degree by k, say, and then the c epsilon k. And there is also a question. This was actually first done by Pila in the real setting, but that technique adapts quite directly. And then there is this question that I already raised to generalize Vermeulen's technique. If x is inside Cp to the n of dimension bigger than 1, can you also bound? We have no idea yet, but that should be, it's a nice generalization than just looking at x inside Qp to the n. And then there is another question. If x inside Qp to the n is subanalytic plus comes from some Pfaffian differential equations, so the converging power series satisfies some extra differential equations. We don't know yet how to find Bezout theorems in this case, or to find concrete bounds to have Wilkie's conjecture, an analog of Wilkie's conjecture for that situation. We could do it in CT, where that's a complex situation, infinitesimal complex situation, and Gabrielov studied the complex situation with Pfaffian conditions that we could use. So these are some extra remarks and questions. And if it's okay for you, I would like to do now a coda to this transcendental part. So this was counting Q rational points on transcendental parts. And in the coda, I would like to raise a question about counting Q rational points on algebraic objects. So switch to that setting for like 5 minutes.
Sorry if you have said that. All the examples on the other blackboard fall into this 1H minimal setting?
Yes, they are all examples. They are special cases of the 1H minimal setting. Yeah.
So also the positive characteristic ones?
No, because
but all the characteristic ones.
Yes, and then uniformly, you can do it uniformly, periodically, and so you recover the FPT, the positive characteristic ones, for large P.
Okay.
Yeah, we don't have a candidate notion in positive characteristic of any nice geometry in model theory. Yeah. So, if you count points on algebraic objects, rational points, it's a totally different game. You usually don't reparameterize a la Gromov-Yondin or Pila-Wilkie. You have many techniques and a long history of study. But let me focus on the case of a curve that we maybe call C in P2. It's a curve, and it's an irreducible curve, say, and reduced irreducible integral curve of degree d. Usually I assume degree is 1. And then on that curve, I don't need to look at the transcendental part because that would be empty. But I take the Q rational points. So these are of age, of height at most h, yeah, why not h? Sometimes one writes b for a box. And that means you look at homogeneous coordinates on P2, you take homogeneous integer coordinates which lie between minus h and h, and which lie on the curve, and then you count. The question I will raise also makes sense for hypersurfaces there is a variant of that question for hypersurfaces in N. There is a rather recent result by Miguel Walsh, which bounds this by a constant depending only on d times b to the power 2 over d. And why do I say Miguel Walsh? Well, it was an improvement by Walsh of previous results by Pila and also by Heath-Brown, who had an extra factor b to the epsilon. So they had 2d plus epsilon. Walsh removed epsilon in this case. Of course, for many curves, if you know that the genus is 2 or higher, then you get finiteness by faultings and so on. But that's not the point. The point here is that it works for any genus, but also completely uniformly, because faultings is difficult to make it uniform. Here it doesn't depend on the equation for the curve at all. It only depends on the degree. So it's completely uniform. Even in the faultings case, it says something, or it could say something.
What is B? It's H?
It's H, yeah. H is B. In this context, one works with the box notation more often, so let me stick to that. And then there was a small improvement with Philip Dittman, who is here, Kastrik, and myself, and MVM, who made this constant explicit. So we could do it b to the 4 times a constant which is absolute now. That's the same upper bound. But is this optimal, this t to the 4? We could just show a worst case lower bound, which holds sometimes. The lower bound does not hold always, of course, which is d square times b to the 2 over t. And then also times a non-zero constant. So d square we found as a lower bound, and d4 as an upper bound. And then there was a question by Per Zalberger whether the d square could also be found as an upper bound. And this is what we did at the cost of having a new logarithmic factor. So we introduced the b to the epsilon in the logarithmic form to some kappa by Benjamini, Novikov, and myself, and then generalized with Kato to higher dimensions also. And then you can ask, is this optimal? well, sometimes this is better, sometimes this is better, but they both hold completely generally. But this becomes interesting, of course, when d is bigger than log b to some power. When d is bigger, it's really big, then this becomes much sharper than that. But can you do better? And then we found another worst case lower bound, and there is another trivial upper bound. For the same count, you can never have more than b to the power 3 times points, 1 second, because on the projective plane you have b to the 3, you have 3 homogeneous coordinates, there are b to the 3 integral points at co-rational points at most, so you can never become bigger than this. So this, for example, this wins when d is bigger than b squared, for example. This becomes really bad. This would be already b to the 4. Was there a question?
What does k depend on? Is it just some, like in the log?
12. It can take up to be 12. In this case. Some absolute constant. Absolute constant. So sometimes the bounds that you have, they become worse than trivial bound or a total count. And we also have another kind of, and this lower bound, we found it when d is roughly the same size as b. Then this becomes d squared actually. We found this. But what in the range where d is bigger than b and less than d squared, say, can we do something better than both bounds that are on the board? And so we found a worst case lower bound already, which is d times b. D times b times a constant also. And this holds sometimes in the worst case for some values where, this is b squared, where d gets close to b squared, you can really find db. It's a lower bound, so the question is now, can we also have that as an upper bound? So this very same count of q rational points of height b. Can you bound it by c db? And then also some logarithms, possibly some k prime, so the db. And that would be better than everything that's on the board in a certain range for b. And it's linear in the degree, which means that it's handy to use because it's additive in the degree, so it could even work for some reducible curves. And this is a question mark here that I want to raise. It's in the work with Loeser. Loeser and myself will raise this question because we do this lower bound and we have a similar question in all dimensions for hypersurfaces. We think that our construction of lower bounds is possibly optimal, so that's why we ask that the d square can be improved to the CDB. So the CDB would hold always, but of course it's not always better than the other bounds. But in some range it would be the best, no better bound. That's the CDB. And in the same paper we show that you can already improve it a little bit. You get c d to the 4/3 times b. So this is the paper with Loeser. We already get towards the CDB bound with the 4/3. But that's just an easy observation, following from the other situations and some small analysis. So this is easy, but to get it down to CDB seems to be a much bigger challenge. And let me to end also formulate a question for hypersurfaces in P to the n. In P to the n you can count the two rational points of height at most b. With Kato and Bignamini we showed an upper bound d squared times the dimension growth typical bound, namely dimension of x. Here as a hypersurface n-1 times some logarithm, double prime. But we think, in general, it can be improved to minus 2 over n. And then times b to the dimension x, and the logarithms also. So the quadratic dependence on d, we think it's not optimal and it could be subquadratic. In the limit, of course, it becomes close to quadratic, high dimension. And for curves, the 2 minus 1 would become exactly the t to the 1. So that's where I would like to end. Thank you.